Everyone, I'm Stella Ocker. I'm a grad student at Cornell University working with Jim Cordes and Shami Chatterjee. And today I'll be talking to you about constraining galaxy halos from the dispersion and scattering of fast radio bursts and pulsars. So this work is currently in preprint form on the archive and submitted to AppJ. And feel free to reach out to me afterwards if you have any lingering thoughts or questions about this material. And also I should say, I am not going to be able to monitor the chat or hand, but also if you have a question at any point during the talk, feel free to just speak up and interrupt me. Okay, so FRBs are for the most part extragalactic, and they propagate through a whole slew of media along their journey from the source to our detector. So this diagram is just highlighting some of those key components along the FRB's journey, right? And along their journey, they experience various propagation effects like dispersion and scattering, which arise from electron density fluctuations in the ionized media along the line of sight. And the total amount of scattering that we ultimately observe is the product of the FRB's whole journey, but certain media along the line of sight can contribute more or less or even entirely dominate the scattering that we observe, right? And so for most of the FRBs that we consider, it turns out that the interstellar medium of, for example, our own galaxy or the host galaxy seem to dominate the scattering that's observed. But in this work, we're really concerned with constraining how much scattering comes from galaxy halos. So our main goal was to first constrain the scattering contribution of the Milky Way halo. And to do this, we really need to leverage our knowledge of the galactic ISM and its scattering contribution using the pulsar population. And then using that knowledge in tandem with scattering observations of two FRBs, 121102 and 180916, to place a constraint on the amount of scattering from the galactic halo. And I'll motivate why we use these two FRBs later on. And then finally, we extrapolate that analysis to the case of galaxy halos that are in between the Milky Way and the host galaxy. And we look at two specific cases of FRBs that pass through intervening halos, 181112 and 191108. And so just to give you a broad brush overview of where we're going, I'll start out by talking about how electron density fluctuations actually relate to the scattering that we observe. Then I'll talk about how we model the electron density of a galaxy halo and get an estimate of the dispersion measure. Then going on to talking about our constraints for scattering in the Milky Way halo, and then finally onto extragalactic halos. So any FRB, when it passes through the Milky Way, will, broadly speaking, encounter two main parts of the Milky Way. It will encounter the halo and the galactic disk. And so the galactic disk can be broken up into two main components, a thin disk and a thick disk. And the thin disk contains most of the galaxy star formation, the spiral arms, and it lies relatively close to the galactic plane. While the thick disk contains mainly the warm ionized medium, it's more diffuse, less dense, and it extends about 1.5 kiloparsecs above the galactic plane. And so we know the electron density distribution of the galactic disk fairly well, thanks to, in part, a large and well-studied population of galactic pulsars. Now, our galactic halo, our knowledge of the electron density of the galactic halo comes predominantly from oxygen absorption lines and X-ray emission maps, and it's thought to be dominated by the hot ionized medium. So it's much less dense, more diffuse, and it extends a few hundreds of kiloparsecs out from the galactic center. And so when we think about the FRB dispersion budget, we're used to thinking in terms of this trade-off between the density of a medium and the path length through it, right? And so even though the halo is much less dense than the galactic disk, an FRB travels a much longer path length through it. So we do end up seeing a non-negligible contribution from our galactic halo to an FRB DM. right? And so you have to think about the same sort of trade-off when it comes to FRB scattering, but you have an additional component, which is the geometric configuration of the source, the scattering lens, and the observer. And so how do we actually get from electron density fluctuations to observed scattering? Well, we model the ionized medium using what's called the cloudlet model. And so here we have cloudlets of ionized gas. The variance of electron density fluctuations within a cloudlet is given by epsilon squared. The variations in the mean density from cloud to cloud is given by this parameter zeta. And then the cloudlets have a volume filling factor F, and the electron density fluctuations follow a power law wave number spectrum, which traces the underlying turbulence driving these density fluctuations. And so the electron density fluctuations gave rise to scattering. We have three main scattering observables: pulse broadening, scintillation bandwidth, and angular broadening. This diagram in the middle is showing you arbitrary rays in black launched from a source at S, and then these colored lines represent the rays that actually reach the observer. And so you can see straight away that the longest path length rays correspond to the widest angles of arrival, right? And so you end up seeing temporal broadening from these longer ray paths arriving at later times. You see scintillation arising from the interference between the different rays converging at the observer, and you see angular broadening. And then this diagram on the left is showing you a typical two-screen geometry, which we think is actually the kind of scattering geometry that applies to many FRBs. And so this red curve is showing you the width of the ray bundles that actually arrive at the observer. And so in this cloudlet model, the relationship between pulse broadening and dispersion measured DM is actually really simple. The pulse broadening is related to DM squared by the fluctuation parameter F tilde. And so the fluctuation parameter is directly related to the electron density fluctuation statistic, and it's related to the filling factor and the outer and inner scales of the turbulence wave number spectrum. And so the fluctuation parameter concisely represents the internal properties of the ionized clouds. And then the pulse broadening is also related to these other scattering observables. Pulse broadening is inversely related to the scintillation bandwidth through the uncertainty principle, and you can relate the scintillation bandwidth and the angular broadening by the distance to the scattering screen. And so this, of course, applies to a single screen geometry. Now, there are a few other factors in this equation. You have the observing frequency nu, and then you also have this factor A tau and G scat. Oh, and then I should also say that when you're applying this equation to scattering in an extragalactic screen, you have to correct for the redshift of the scattering material. So now I'll briefly explain what those other factors are. So the pulse broadening time shown here is equivalent to the 1/e time that's typically measured when you fit an exponential scattering tail to a pulse. But that 1/e time assumes that the scattered image is Gaussian in form. And so this is not generally the case. And when you have non-Gaussian scattered images, the mean temporal delay is actually going to be longer than the 1/e time. And so this correction factor A tau essentially takes the mean delay and corrects it to be the 1/e time. And so it will be less than or equal to 1. And the exact value of A tau depends on the spectral index of the turbulence wave number spectrum. And it also depends on the ratio of the inner scale to the diffractive scale. And so we don't in practice know these parameters for a given medium. And so we just believe symbolically A tau in our equation and propagate it through. So the other main factor here is G scat. And G scat represents the relative configuration of the lens, the source, and the observer. And so this plot here is just showing you G scat as a function of lens redshift. for a constant host redshift of 0.5 and a constant path length through the lens of 600 kiloparsecs. And so as you can see, the leverage from GSCAT is largest about halfway between the source and the observer, right? But the total amount of scattering that we see is not just dependent on GSCAT, it also depends on all of these other factors. And so the last piece of the puzzle is the dispersion measure, DM. Right, so the dispersion measure is the integrated electron column density, and the electron density distribution of our own galactic halo is not extremely well constrained by observations. Models generally take the following approach. We assume that the baryons trace the underlying dark matter distribution, and so the baryons account for some given fraction of the total halo mass. And so we adopt the modified Navarro-Frank-White profile from Prochaska and Zhang 2019. And so this profile describes the dark matter density profile of the galactic halo. And the electron density distribution for the Milky Way halo that's predicted by this model is shown here on the right. And so this blue curve is showing you the numerical roll-off that we implement when we actually integrate over the electron density to get a DM. And so the DM predicted by this model is about 60 parsecs per cubic centimeter. This is fairly similar to the predictions of other galactic halo density models. But currently, observations allow the DM of our own galactic halo to range anywhere from 10 parsecs per cubic centimeter up to 100 parsecs per cubic centimeter. So it's not extremely well constrained right now. And so whenever we present given results, we try to make it explicit when we assume a certain DM value for a halo. And we also try to present our results as much as possible without a given DM assumption. So how do we actually take all of that and get to a scattering constraint for the Milky Way halo? Well, our approach is fairly simple. We just take the scattering from the galactic halo and approximate it as less than or equal to the total scattering that's observed minus the amount of scattering that's coming from the galactic disk. And so we can constrain the amount of scattering from the galactic disk using the pulsar population and the galactic electron density model, NE 2001. And then we can use multiple FRB scattering measurements and perform a joint likelihood analysis to get a constraint on the scattering from the halo. And this ultimately gives us an upper limit on the fluctuation parameter times DM squared for the halo. And so then once we have this constraint, we can make a further assumption about what DM is for the halo to get an individual constraint on F tilde, the fluctuation parameter. So to get at this constraint for the halo, we first have to consider how much scattering is coming from the galactic disk. So here on the left, I'm showing you the distribution of tau over DM squared for all galactic pulsars that have scattering measurements as a function of galactic latitude. And you can see the equivalent value of F tilde on the right-hand axis. And so this blue band is showing you the mean value of the fluctuation parameter for the thick disk, which dominates lines of sight at latitudes above 20 degrees. Now you can also see that there's this orders of magnitude increase in F tilde as you move to lower latitudes, and in particular towards lines of sight through the inner galaxy, which are indicated in orange. And so this huge variation in the fluctuation parameter between different regions of the galaxy will come up later. Now, to get from a constraint on F tilde for the thick disk to a constraint on pulse broadening, we need to know the DM contribution of the thick disk. And so here on the right, I'm showing you DM versus latitude for all galactic pulsars. And this black line is showing you the maximum DM contribution of the thick disk. And so when we take this maximum DM for the thick disk and combine it with our constraint on F tilde, we get a maximum amount of pulse broadening from the thick disk And this is on the order of tens to hundreds of nanoseconds at 1 gigahertz. And so on the high end, you've got about 0.1 microseconds at most, and that response latitudes around 20 degrees. And then as you move up to higher latitudes, you'll get a scattering time on the order of 10 to 20 nanoseconds. Okay, so very little scattering from the thick disk is the bottom line. So we next look at the scattering measurements of two FRBs, 1102 and 180916. So why these two FRBs? Well, the main reason is that they arguably have the most comprehensive and precise array of scattering measurements currently available. And so these scattering measurements are shown in this table down here. And you can see for FRB 121102, we have the whole array of scattering measurements. And in particular, there are multiple measurements of the scintillation bandwidth at different frequencies. So this is what's shown on this plot to the right. We have the scintillation bandwidth versus observing frequency from various studies. And these solid lines show linearly square fits to the frequency dependence. And so you can see that the frequency dependence is fairly consistent with what we would expect from interstellar scattering. So I'm also showing down here the scattering predictions from NE 2001. And for both of these FRBs, you can see that the predicted scattering is slightly smaller than the scattering that's actually observed. And so our approach is to basically assume that that amount of excess scattering is the maximum amount of scattering that could come from the galactic disk. So I should also say that for FRB 121102, we can say with a high degree of confidence that the scattering is dominated by the galactic disk and more specifically by the outer spiral arm. And we can do this because we have both a scintillation bandwidth and angular broadening measurement. And so these two measurements are related to each other by the distance to the scattering material. And so here on the left, I'm showing you the angular broadening versus distance to scattering screen. And this blue region is showing you the angular broadening measurement from Marcotti et al. 2017. And then this green curve is showing you the angular broadening versus distance that's implied by the scintillation bandwidth measurement. And so the overlap of these two regions corresponds to the distance to the scattering screen. And so this region is shown on the right here in gray, and this plot is showing you the dm electron density and cn squared, which is the amplitude of the turbulence spectrum, as a function of path lengths from the solar system, as predicted by NE 2001 for this line of sight. And so you can see that the distance to the scattering material is consistent with the outer spiral arm, which lies at about 2 kiloparsecs. And it lies well within the galactic disk, which extends out to about 15 kiloparsecs. And so for this FRB, we can say that the scattering is almost entirely coming from the outer spiral arm and galactic disk. And so we really don't expect much scattering to be allowed from the galactic halo along this line of sight. Okay, so we also look at the scattering predictions from YMW16, another galactic electron density model. And in both of these cases, it turns out that YMW16 drastically overpredicts the scattering of these FRBs. And it does this for a number of other FRBs as well. And in the paper, we go into a somewhat in-depth discussion of how much YMW16 overpredicts extragalactic scattering and why. And so here I'll just give you a kind of a broad brush overview of the main reasons. So the first, YMW16 doesn't explicitly predict scattering based on electron density fluctuations. Instead, it predicts scattering from a DM using the tau DM relation. And so this plot on the right is showing you the pulse broadening time versus DM for galactic pulsars and also a handful of FRBs in red. And then this red curve is showing you the empirical best fit relation. which is given by this equation up here. And so this is the classic hockey stick diagram in which the pulse broadening time has a much shallower dependence on DM for lower DM objects than it does for higher DM objects. And as you can see, this plot is a little outdated, but this is still true today. Most FRBs fall in the high DM part of this diagram, but their scattering tends to be over-predicted by the tau DM relationship for galactic pulsars. And so there are two main reasons for why the tau DM relation based on galactic pulsars over-predicts FRB scattering, and I'll go into that now. So the first reason is essentially comes down to the difference between spherical and plane wave scattering. And so when we think about pulses from a galactic pulsar, they are diverging spherical waves. And the same is true for an FRB at the source, but FRBs travel over such long distances that by the time they reach the observer, they are essentially planar. And so what this means is that galactic plasma will actually scatter the extragalactic planar waves more than they would a source of spherical waves within the galaxy. And so this is being represented in this diagram on the left, where you can see that the plane waves get scattered from wider angles than the diverging spherical waves do from a source inside the scattering medium. So it turns out that YMW16 inaccurately corrects for this difference between spherical and plane wave scattering. So this is one of the reasons why it overpredicts FRB scattering. And so the other reason comes down to why the tau DM relation is steeper at high DMs than it is at low DMs. So this high DM part of the tau DM relationship largely applies to lines of sight through the inner galaxy, right, where pulsar DMs tend to be higher. And we can see this reflected in the distribution of the fluctuation parameter versus latitude, right? So earlier I pointed you to this orders of magnitude increase in F tilde at low latitudes and towards the inner galaxy. And this huge increase in F tilde is directly responsible for this steepening of the tau DM relationship at higher DMs. And so most FRBs are not seen through lines of sight through the inner galaxy. So using the part of the tau DM relation that applies to those lines of sight would really be inaccurate and would in fact overpredict the FRB scattering. So it would potentially be better to instead use the low DM part of the tau DM relationship if you want to use the tau DM relation to predict the scattering of FRBs from their DMs. Okay, so long story short, we proceed by using the NE 2001 predictions for the amount of scattering that's coming from the galactic disk. And we subtract that from the total scattering that's observed for FRBs 121102 and 180916. And we run that through a joint likelihood analysis to get a constraint on F tilde times DM squared for the galactic halo. And so this plot in the middle is showing you the probability density function for F tilde times DM squared. And this upper limit implies a maximum amount of pulse broadening from the galactic halo of 12 microseconds at 1 gigahertz. And I should also say that this upper limit is probably fairly conservative, precisely because 121102 shows such strong evidence of virtually all of its scattering coming from the galactic disk, as I showed you earlier. So to actually get at an individual constraint on the fluctuation parameter, we need to make some assumption about the DM of the Milky Way halo. And so we adopt a very generic approach where we approximate the DM using a Gaussian PDF with a mean of 60 parsecs per cubic centimeter. And we just do this because it just generally approximates the range of allowed values for the DM contribution of our halo. And so when we combine this dm contribution of the halo with f tilde of the halo, or f tilde times dm squared of the halo, then we get an upper limit on the fluctuation parameter. And so we find that f tilde for the Milky Way halo is less than 0.03, and that number probably doesn't mean much to you right now. So first, we should place it in context. So I'll first talk about the two other FRBs that we look at, which have halos intervening their lines of sight. And so the first one is FRB 181112. And so this image on the right is showing you an optical image of the host galaxy here. This orange ellipse is showing the localization of the FRB, which was found by ASCAP. And it's associated with the host galaxy at a redshift of 0.48. And as you can see, it comes within 29 kiloparsecs of a foreground galaxy at a redshift of 0.37. And so there's a fairly strong constraint on the pulse broadening for this FRB. It has a pulse broadening time of 21 microseconds at 1.3 gigahertz based on this first burst component shown here. And so we adopt the simplest approach, which is just to say that this amount of pulse broadening is the maximum amount of scattering that could be contributed by this foreground halo. And so we essentially treat the pulse broadening as an upper limit on scattering from the halo. And then we use that to infer an upper limit on f tilde times dm squared for the halo. And then using the modified NSW profile to model the dm contribution of that halo, we can get an upper limit on f tilde. And so before I show you that result, I'll talk about the other FRB that we look at, which is 191108. So this plot on the left is showing you the optical image. The FRB was localized as shown in this red line, and it was discovered by FRBs, but unfortunately there's no host galaxy association as of yet. So it has a redshift upper limit of 0.52 based on the DM redshift relation. And as you can see, it passes within 18 kiloparsecs of the M33 halo, which is 840 kiloparsecs away. And so on the right here, we have the burst profile, and no strong evidence of scattering is seen in the burst profile. But they do estimate a decorrelation bandwidth. So this plot is showing here the autocorrelation function of the burst spectrum. And from it, they estimate a decorrelation bandwidth of 40 megahertz, which is indicated by this red line. And so one major caveat to this estimate is that they don't see 100% intensity modulation, which is generally what you'd expect from diffractive interstellar scintillation of a point source. And so one way that you can explain this is if this bandwidth does correspond to scintillation in the M33 halo, then you would need an additional screen somewhere between the source and M33 that essentially smears out the point source and quenches the intensity modulation in the halo. So we again just proceed by assuming that this measurement accounts for the maximum amount of scattering that could be contributed by M33 halo, and then use that to place an upper limit on the fluctuation parameter for the halo, again, by assuming a DM model for the halo. So let's put this all together. So this plot is showing you the fluctuation parameter for all of the objects that we consider. And so up here, we have the upper limit for M33, the foreground halo of 181112, and the galactic halo. And these green error bars essentially actually demonstrate the range of allowed values for F tilde based on our uncertainty in the DM contribution of the halo. And these orange error bars represent the range of allowed values for F tilde based on this range of possible values for a tau, that factor that translates the mean temporal delay to a 1/e scattering time. And then again, as I mentioned, for each of these halos, we essentially treat the scattering as upper limits to place an upper limit on the fluctuation parameter in each of these cases. So I show you a few other values of F tilde here. You'll find the value of F tilde for the galactic thick disk based on the galactic pulsar population. And then I have two values that are characteristic for the galactic anticenter and the inner galaxy based on NE 2001. And then lastly, I have a value here of F tilde for the Large Magellanic Cloud, and this is based on the scattering of BO 540 -69, which is currently the only LMC pulsar that has a published scattering measurement. So, oh, and then I should also mention that over here on the right, I've put the equivalent limits on the pulse broadening in milliseconds at 1 gigahertz. And that in each of these cases considered in the paper, we present our results first as the fluctuation parameter times DM squared, so that in the future, if better constraints on the DM are obtained for these halos, then we can go back to our original results and easily use them. So one of the first things that you'll notice on this plot is that the fluctuation parameter is largest for the inner galaxy and the LMC. And so for the inner galaxy, it makes sense for the fluctuation parameter to be larger here than in the anticenter or thick disk, because the inner galaxy contains far more H2 regions. And so you generally expect larger density fluctuations here than towards the anticenter or thick disk. And for the LMC, this pulsar actually lies inside a supernova remnant, which is an enhanced scattering region. So again, it's not particularly surprising that the fluctuation parameter is much larger here. And so the next thing you'll notice is that our constraint for the galactic thick disk actually falls below our upper limit on the fluctuation parameter for the galactic halo. And we know the thick disk is dominated by the warm ionized medium. And so if the galactic halo is dominated by the hot ionized medium, we would really expect the fluctuation parameter in the thick disk to be larger than in the galactic halo. And so let me break that down a little further. I'll remind you that the fluctuation parameter is related to the density fluctuation statistics, the filling factor and the outer and inner scales of turbulence. And in the hot ionized medium, we have a temperature on the order of 10 to the 6 Kelvin, a large filling factor, an outer scale that's roughly from hundreds to thousands of parsecs, and an inner scale that's more like tens to hundreds of parsecs. And so generally, we'd expect the fluctuation parameter to be much smaller here than in the warm ionized medium, where the filling factor is much less than 1. The outer scale is around tens of parsecs, and the inner scale is around tens to hundreds of kilometers. And so based on this generalization, we would really expect for the fluctuation parameter of the galactic halo to be smaller than the galactic thick disk. And so is there any physical significance to attribute to the fact that our upper limit for the halo falls above our constraint on the thick disk? Probably not. This upper limit for the galactic halo is probably not very constraining, right? It's only based on 2 lines of sight, FRBs 121102 and 180916. As I said before, this is probably more conservative because FRB 121102 indicates that the galactic disk really dominates the line of sight in that direction. But we really need to extend this to more FRBs because we certainly expect the fluctuation parameter to vary between different lines of sight through the halo. And so with more FRBs, we'll get a better sense of what the average fluctuation parameter of the halo is. And so the other thing is that the constraints on F tilde for these other galaxy halos are quite small and indicate that very little scattering is occurring in either of these galaxy halos. And so this might seem kind of surprising if you're a proponent of the clumpy CGM model. So there is increasing evidence from quasar absorption studies that the circumgalactic medium is not just the hot ionized medium, but in fact also contains cooler 10 to the 4 Kelvin gas that has a very low volume filling factor, but extends out as far as the virial radius of the halo. So this diagram is showing you one kind of typical model of the clumpy CGM, or as Vedantam and Finney call it, the CGM fog. And so you can see this cooler gas with very low filling factor embedded in this hot medium. And so when we take the filling factor and scale sizes that are used in this model and apply it to our fluctuation parameter, we actually find that the fluctuation parameter implied is orders of magnitude larger than our upper limits for the galaxy halos that we consider. And I'll also say that this model predicts a fairly large amount of scattering. It predicts a pulse broadening time greater than 1 millisecond at 1 gigahertz for FRBs with host redshift larger than 1. And this large scattering largely arises from the fact that this cooler gas in this model has a very large areal covering fraction. So it extends over a large fraction of the area of the halo. So this suggests that the clumpy CGM, at least in the formalism of the Vedantam and Finney model, is not necessarily favored for the lines of sight that we consider. Now, this doesn't entirely rule it out. There is a good deal of room for playing around with the filling factor and the various scale sizes. And so it doesn't seem to be favored by the small fluctuation parameters that we find, but not necessarily ruled out. And I also want to say that the fluctuation parameter is a fairly useful diagnostic for this because it's insensitive to a broad range of assumptions about the scattering medium, right? So you don't have to assume that the halo is cooler and clumpier or hotter and more diffuse in order to get a constraint on the fluctuation parameter. Instead, you just calculate the fluctuation parameter directly from your scattering measurement. So you can let this fluctuation parameter kind of diagnose the properties of the halo for you. And in particular, you can see it as a useful metric for comparing the internal properties of different galaxies and of different regions of our own galaxy. So I will just briefly summarize. The fluctuation parameter, as I just said, is fairly straightforward to calculate from scattering measurements. At least for the lines of sight that we consider, we see a small to negligible amount of scattering from galaxy halos, at least those considered here. But certainly expanding this analysis to a larger sample of FRBs will be really interesting. And more broadly, FRBs show a pretty large range of scattering. Some FRBs show a lot of scattering, some FRBs don't show very much. And so you kind of maybe naively expect that as a result, any scattering medium that all FRBs travel through would be ruled out as the dominant source of FRB scattering. And so it would be interesting to see whether the FRB scattering that we observe is actually related in some way to the location of the FRB source relative to its host galaxy. And so another project that Jim Cordes is working on with Shami and I is actually using the relationship between tau and DM to place improved constraints on the DM contribution of FRB host galaxies with the aim of improving the accuracy of the DM redshift relation. And one of the things that we're finding for the FRBs that we're looking at is that in most cases, the FRB scattering seems to be dominated by the host galaxy and by the Milky Way galaxy. So yeah, that's it. I would be happy to take any questions.
Awesome, thank you, Stella. That was really interesting. Are there any questions? You can either use the raise hand thing in Zoom or just speak up. I had one question about future observations. So sort of what kind of ideal FRB measurement could constrain this better? Like if you had an FRB that you had definitely like pinpointed to a galaxy and had identified like an intervening halo, with like absolute certainty or something, like, would that be like the most useful, or is there like a more useful observation, like a more useful specific FRB orientation case that would be useful for this?
Oh, so yeah, so that would certainly be really useful. Are you asking more on like along the lines of like what configuration of like FRB host versus foreground would be useful?
Yeah.
Mm-hmm. Yeah, I mean, I think it would definitely be useful to have kind of a range of FRBs with like different impact parameters from foreground galaxies, so that you could, get a better sense of like how significant the amount of scattering observed relates to their orientation relative to the intervening galaxy. It's, both of the cases that we consider here, 181112 and 191108, they do have fairly small impact parameters, like they're well within the virial radius of the foreground halo, but even then we don't see very much scattering. So it would certainly be interesting to see a case with an even smaller impact parameter, where we would expect maybe the ISM of that foreground galaxy to have a significant contribution. Yeah, and then I mean, like always having host galaxy associations and localizations is useful. So it's just like always the case. And then I will say more broadly from a measurement point of view, it's really useful to have like multiple scattering measurements available, some combination of both a scintillation bandwidth and an angular broadening, or scintillation bandwidth and a pulse broadening, because then you can really start to pick apart the scattering geometry and see, are there multiple screens here? Are the scattering measurements self-consistent or not? Does their frequency dependence conform to what we would expect? That kind of thing.
Thanks. That's really helpful. All right, are there any other questions?
Just a quick comment that for CHIME in particular, with the large number of low frequency scattering measurements that are going to come out, those will be super interesting, but it would be even more interesting if they had precise localization so that we could say which part of the halo was being probed.
Okay, other questions? All right, if not, thank you so much for this talk, Stella. It's really interesting, really great work, and we really appreciate you taking the time to come speak with us. And we've recorded the talk, and we will make it available online if that's okay with you, so that other people in our collaboration can enjoy it. So I will